Hello and welcome to Learn Data. It's great to have you back on this channel. I'm Nilesh, and in this video we'll continue learning about pandas. In the previous videos, I hope you learned about descriptive statistics and how the calculations are done in the background, such as for mean, standard deviation, covariance, correlation, etc. And now you'll have a much clearer picture of what's actually happening when we run the code in Python. So in this video, based on what you've already learned from those videos, we'll look at how to write a code to calculate percentage change, covariance, and correlation. And this would be for both series and data frames. So let's get into a Jupyter notebook and start coding. Here I've already created a new notebook and imported these libraries. We just need NumPy and pandas, and for data we do not have any specific data sets, so we'll create series and data frames as we go along. So the first item that we are going to look at is percent change, and for this we'll create a small series pd.series. Here we'll add some numbers 2, 1, 3, 3, maybe 4 and 5. So this is the series A that we have created. Now if we want to find the percent changes from the value at index 2, value of index 0, which is 2, to value at index 1, which is 1, then value at index 2, which is 3. So how do we do that? It is very easy in Python pandas. So what we can do is type a.pct underscore change, open close parenthesis, and this will give us the percent change. So going from 2 to 1, so this would be the way. If you remember from the videos for descriptive statistics, what we would be doing here is we are calculating the percent change based on the number 2. So here we would have 1 minus 2 divided by 2, and that's the 0.5 we have right here at index 1. And similarly for the second one, this would be, and the new value is 3, and we have minus 1 divided by the old value is 1, and thus we have the 2, which is right here. So this number that you see here, it's in decimal, and if you're looking, so you need to multiply it by 100 to get the actual percent that you know of. So there's a 50% decrease when you go from index 0 to index 1, and that's denoted by the negative sign here. For all increases, it's always a plus sign, and at index 3 we can see that the values didn't change, so therefore the percent change is 0. Similar here, what we can also do is, here we have calculated the percentage between all consecutive numbers, 2, 1, 3, 3. We can skip some of them if we want to, and to do that what we would type is a.pct underscore change, and here we can specify how much we want to skip, or by supplying a number to this period is equal to, and if we specify 2 and run this, percent change, let's look at the error. Shift got an unexpected keyword on period, so it should be periods, sorry. Now if we look here, we are skipping 2 numbers, so there's nothing before 2, so the NN is for that. The second is 1, and therefore we have the NN for that. And the third at index 2 we have 3, and that 3 is 3 has a value of 2, and that 2 is coming from these numbers, so 2 and 3. So if you calculate those two numbers, so 3 minus 2 divided by 2, then you have 0.5, and that's exactly what we have here, this 0.5. So that percentage change is from the index 0 to index 2. So it's hopping over this 1 and going directly to 2. Similar to series, we can also calculate the percentage changes for a data frame. So if you type, let's go ahead and create a data frame df. So pd.dataframe, and here we'll create a couple of columns. So column A, will put the same series A, and then column B, we can go ahead and create the column A squared. Now if we look at our data frame, this is the data frame we have, and here if we are trying to calculate the percent changes, we would type df.pct_change, and when we run this, we can get the same similar values back for each of the columns that we have right here. So the column A would have the same values as we did for the series A, minus 0.5 to 0.3, so minus 50, 20, this is 200, so 2, and then 0, 33, 25. That's what we have here. If we multiply this by 100, so you'll see the exact same numbers. Similar to the series, when we are working with a data frame and we are trying to calculate the percent change, we can also specify the periods here as well, and we can get the similar output as we saw before with the data frames. Next, let's look at covariance. And for this, we are going to create another series B and use that one. So B is equal to pd.series, let's say 4, 5, another 5, and 7, 8, 6. So that's the series B we have, and we'll go ahead and create another data frame df1 using this series and the series A that we had earlier. So df1 is equal to pd.dataframe, and here we have capital A is equal to colon A, and A1, for A1 we'll have maybe a square of A, and then for B we'll use the B series that we created just now, and for B1 here again we can go ahead and just use the square of the series B as for the B1 column. And if we look at the data frame, this is the new data frame that we have. Now if you remember from the descriptive statistics videos, covariance is basically you are subtracting the mean from the observations, and then from each columns multiplying them together, then summing those numbers and dividing it by n-1. So here all that is done in just one line of code. So if you are trying to calculate the covariance between series A and series B, you would simply type a.covb, and that's it. It's that simple. And similarly, if you're trying to calculate the covariance for the columns in a data frame, you would simply type df1.cov and open close parenthesis, and here we get a matrix back, and what this matrix is telling us is that along the diagonal, that's the variance. So variance for just each separate column. So if we want to calculate it, what we can do is use the series A, which was the same as column A. So A minus np.mean of A, and then we want to square that, and then take a sum of that, np.sum, and then we want to divide this by n-1, as you may remember from the video. And here we have 2, which is the variance for the column A. Similarly, we can go ahead and calculate it for the column B, which was actually the series B, and we have 2.166, and that's what we have here. So the diagonal is the variance, and off diagonal values are covariance, and the 12 indicates the covariance between column A and column A1, and then 6.733 indicates the covariance between column B and column A1, and so on and so forth for all other columns. Here if you see, all the signs are positive. It means the direction of the relationship is in the positive direction. So if one is increasing, the other one is also increasing. So for example, between A and A1, we can see that overall, as A is increasing, A1 is also increasing. Next, moving on, let's look at additional things we can do with the covariance, how we can handle NA values in this particular method. So for the data frame that we have, which is df1, what we'll do is we'll go ahead and create some NaN values, and let's go and use iloc. And here for row, let's say is from 2 to 4 and columns 0 to 2. We'll go ahead and put np.nan, and then again using the iloc, let's say from 3 to 5 and 2 to 4. We'll go ahead and put np.nan. So now when we look at our data frame df1, it looks like this. It has a bunch of NaN values. Here if we calculate the covariance, so if we say dfv.cov and run this, we do get the covariance back where the NaNs are ignored. But if you are in a situation where you need to have certain number of numbers in the calculation, then you can set it by using the minimum periods. For example, here we have only 4 numbers, but if you want, say you had to have 5 numbers in the column to calculate the covariance, then if you have just 4, you'll get a NaN. Let's see how that works. So df1.curve, and here we can specify min underscore periods is equal to, if we put 3, we'll get the answer back, because there are 3 values at least which are not NaNs, right? Now if you put a number of 4, it will still work, but if you put 5, we are going to get NaN back, because there are no 5 values there which do not have NaNs in that. Moving on, let's look at correlation. And if you remember from the videos of descriptive statistics, there are 3 types of correlation that we had discussed there, which was Pearson's, Spearman, and Kendall. And we can use all those 3 methods in this particular command. The simplest one we can use by default one, that is df correlation. So df a dot corr b, corrb, and here the method that is used is Pearson's. So if you type a dot corr and here you have b, you can specify a method is equal to Pearson's, and so it should be Pearson, and we get the sum number, which is a default value. And just to refresh what you learned from those videos, 0.5 is a very low correlation. Generally, depending on the subject you are in, the experiments that you used to work with, 0.5 is really very low. I would say around above 0.9 would be a correlation where you'd see some relationships between the 2 data sets or 2 series that we have here. But one thing we can definitely see is that here the correlation is positive, which tells us that if one increases, the other is increasing, and we can visualize that as well. So I'm digressing here, but hold on just a minute. matplotlib.pyplot. So from matplotlib. Or import matplotlib.pyplot plt, and here we'll just try to plot A and B, or just put a scatter. And as you can see, there is, so on x-axis we have A, so it does look like they are increasing. If A increases, B does increase. That could be indicative of this positive correlation value that we get. Now, apart from Pearson correlation, there are other methods, which is Spearman and Kendall. All of them work, and we can see that. So a.corr b method is equal to Spearman, and again we have this number. And if you remember, these are ranked correlations, and so the values are different. And the next is Kendall, so this is 0.5 again. Now, similar to the covariance that we calculated earlier, here also we can give minimum periods that are needed. So if we pull our data frame back, df1, now in this data frame, let's first see how we can calculate the correlation between columns. So if we have the column A, and we use .corr, and in parentheses we can type df1, and let's say we use column B maybe, and run this, we get much higher correlation than before of 0.72. And here, if we just want to take a look at this plt.plot, and here we can say df1 dot a and df1 dot b. So if you have, this is another notation where you don't have to create the square brackets and write a code, have the codes there. You can simply say dot a, and it understands that it's the column in that data frame. Now scatter, and this is the values we have. We just have 3 data points because all others have nn either in A or in B. But we do see that as A increases, B seems to be increasing by this point here. Now, if we are trying to calculate the correlation by using the mean periods, what we would do is, just pull the data from df1 back, and here we would say df1 A dot corr, and here we'll have df1 and b. Now min underscore periods is equal to, if you put 2, we do get the value back. But now if you put a number where both of them do not have value, so we have these 2 columns and just 3 columns have values, so 3 will work. But if we put 4, we are going to get an n, because there are only 3 rows in which both A and B columns have values. Others, either A has value or B has an n, or vice versa, or both have n's. So that's why the 4 minimum periods gives us nn. But if you go back and put 2, then we do get the correlation value back, and it is same as what we had before. Now, apart from this, Pandas also has very interesting usage of the corr method or function, where we can provide a custom function to use. So how do we do that? Using a custom function with .corr. And for this, what we can do is create a function. So let's create a function to calculate the correlation, or we calculate the covariance. So df1, this is the data frame we are using, and the function we'll create is def, and we cal covariance, and it takes x and y. Now the x, we'll use this to calculate the difference. So x minus np.mean of x, and then t1, so that's the second column or the second series that comes in, y minus np.mean of y, and then we are going to get the covariance. So covariance is nothing but we take the sum of these two, so sum t1 and t2, so we multiply them, get the sum of that, and after we have the sum, we are going to divide that by length of either t1 or t2, because both of them have the same length, minus 1. So the return value would be just the tqcov. Now one thing to remember here is that when we in this function, it takes in two series, but then the output is only one value. So what it is actually trying to do is going through each column and comparing with all other columns in the data frame. So if we run df1.corr open close parenthesis, and as a method we specify the custom method that we have created, which is calc underscore cov, and run this, then we get the covariance back. So here we can see that 20, 150, 1.5, 15.8. So those are the covariances between these columns. However, the diagonal line is just 1. And you can also visualize how this works. And to do that, what we can do is maybe add a print statement here and print the x, y, t1, t2, and tcov, and then also print a line just to separate the output. When we run this, here we can see that the column A is first compared, which is this, is compared with column A1. Then the column A is compared with column B. And the reason why it's only 3 values, because the rest are NaNs. Both columns should have some value. It cannot be NaN in either NaN in any of those columns. So that's why you just have 3. Then so on and so forth. So here A1, B, B1, then again A1 is compared with so 4, 1, 2, 5, so 4, 1 and 25, it's again compared with B and B1, and then finally B is compared with B1, and those are the values that we get here in the output. So that's a really helpful function. If you have a data frame and you want to apply certain function to get a summarized version of values in a matrix format, then this is really helpful, as we can see. Now let's look at another method, which is corrwith, so corr with, and in this method correlation with, if we have two data frames that have exact same column names and row labels, then we can use this particular method or function. So let's create another data frame df2, which is a copy of df1, so that we know that the labels are the same copy, and we'll go ahead and change the values by making square. Now we have the df1 data frame, which looks like this, and then we have the df2 data frame, which looks like this. They both have identical indices and identical row column names. To run this command, you type df2.corr with df1 or vice versa, and thus you get the correlation values, and this would be Pearson's correlation, which is default for between the column A in the data frame df2 and data frame df1. We can check that by explicitly performing the correlation. So df1.a, and that's the from column A from df2 data frame, and corr df1 A, and method is equal to Pearson, and when we run this, we do see that we have the same output, so 0.98772, and this is rounded off to 30 and what we see up above. So that was it for this video. I hope you learned how to calculate percentage change, covariance and correlation using pandas built-in functions in Python. In the next video, we'll work through window functions and see how those work in pandas. I'll highly recommend that you check out the videos on descriptive statistics so that you get a feel for how the what happens in the background and how to interpret the output for each of these functions or methods we are using in this series in couple of videos now. I'll see you all in the next video. Until then, please like, share and subscribe. Thank you.